Hi folks, welcome back to Physics with Captain Rod. I'm making this video to demonstrate how to use Newton's second law to analyze a system that has multiple parts. So let me talk about what we're looking at here. Alright, so from the movie Jurassic Park here, somebody has trained this T-Rex here to do work for them, and what they've done is they've hooked some sort of collar to it, and this T-Rex is going to pull this system that we have sitting in front of us here. We got this 25 kilogram load that's attached via a rope to a 100 kilogram load that is attached via another rope to this 50 kilogram load. And what we're going to look for here is we're going to try to calculate the tension in each of these ropes, assuming a frictional force of basically 0 along the surface. Now I know that it's probably not it'd be very difficult to have a load configured like this and have a frictional force of 0, but again, just to keep this video as simple as I can, I'm going to assume friction away for this example. So the T-Rex here has ice cleats on or something, and this is an icy surface. I'll make another video here where I talk about how to incorporate frictional forces into it. So in my example here, we're going to assume that this T-Rex can apply a 2,500 Newton force to this load. Now, when you apply Newton's second law, it's very important that you very clearly define your system. And there's several different systems I can define here. And let me just kind of go through some examples here. Let us say that I define this as my system. Remember that forces come in two flavors, basically field forces and contact forces. So we definitely would have a gravitational force down. Then you're looking for direct contacts here. Now there's a contact here between the ground and this orange box. That's going to give us what we call a normal force up. We've got this 2,500 newtons applied right here to the right. But then we have this some sort of force here, which is creating a tension, which I guess I'll call tension 1 in this example. And that tension is going to be to the left on this box. When we write our Newton's second law equation, we're not going to know that tension, and we're not going to know the acceleration of the system. So it's not wrong to start there, but I think we can find a better place to start. If we define this as our system, there are two unknown tensions, one here, one here. So we've got a tension pulling to the right, a tension pulling to the left. Both of those tensions are unknown, and neither of them is this 2,500 newtons. That 2,500 newtons is only applied right here to this mass. So a free body of that middle part of the system also has three unknowns: an unknown tension here, an unknown tension here, and an unknown acceleration. If we define this as our system, we have an unknown tension acting to the right and an unknown acceleration. Now you don't have to do individuals, we can also do pairs. I could do something like this, define this as my system. However, that's going to have an unknown tension here and an unknown acceleration. We could define this as our system. That also is going to have an unknown tension here and an unknown acceleration. Now, if I looked at a pair like this, this rope is an example of what's called an internal force. If I tried to put a force vector in for this rope, that force would be to the right on this mass, but that same force acts to the left on this mass, and the net force on the system inside of this green surface that I've drawn would be 0. So we wouldn't include a tension for this rope right here if this is how we defined our system. But we would have to apply a tension here, an unknown tension, and the unknown acceleration. So none of these examples are incorrect, but I'm going to start with a free body defining my system like this, the whole kit and caboodle basically. So that's going to be my very first free body, and the reason for that is because now both of these tensions are internal forces and they will not show up in the free body. Now whenever you do Newton's second law equations, I strongly recommend that you draw your system. This little computer system is great for this. Okay, so I'm redrawing my picture. I'm going to be very clear about how I define my system now. All right, so this is going to be my system. Now when I draw my free body, this 2,500 Newton force is right here acting to the right. So I'm going to put a force vector in for that. Okay, all right, internal force, internal force. Now, these all have weights. There's a couple ways we can handle it. I could put an mg for each one of these. Or what I'm going to do is I'm just going to lump them all together. I'm going to put one force vector basically in the middle of this. Down equal to mg, and this mass would be the sum of the three, 50, 100, and the 25. Now, also take note there are surfaces in contact right here, here, and here. Those are going to give us forces which are up on each of these masses, and those are examples of what we call normal forces. I'm just going to kind of group those together, call them one force, N, which is up. Now again, this force is the result of three separate forces, one here, one here, one here, acting up on each of these masses. And I think that's it. Again, we don't need to include any forces for what's happening here, because this tension, the force that this rope applies is to the left on this animal, right on this animal. It's an internal force, so it doesn't belong in this free body. Same thing here. If there are frictional forces included, I would include a frictional force, and it would go maybe like that to the left. And again, that would be the frictional force on this surface combined with this surface combined with this surface. Now in this problem we're assuming friction away, so I'm going to go ahead and get rid of that. So this is it. There's the complete free body for the entire system. Now, big thing is, what do we do with the free body? Well, the answer to that is we apply Newton's second law. And in the y direction, it's a pretty boring equation. Sum of all forces in the y direction equals 0, and that's going to tell us that the normal is equal to mg. If we had a frictional force in this problem, we would need that, but here we don't, so I'm not going to bother. I'm just going to go ahead and write a force equation x direction. So sum of all forces x direction equals mass times acceleration, right, positive. And I look at my free body. This is the only force in the x direction, so we got 2,500 newtons equals mass of the system. Now my free body has 175 kilograms of mass, and then times the acceleration. This equation can easily be solved for the acceleration. And we get about 14.3 Newton per kilogram. Now, a Newton per kilogram is a meter over second squared. I'll go ahead and talk about y here, just off to the side. So a Newton over a kilogram. And remember, by Newton's second law, force equals mass times acceleration. So a Newton is a kilogram times a meter over second squared. Right, and then that's divided by a kilogram. So these divide out, leaves us with a meter per second squared. So that T-Rex can really get the job done here. He's pulling quite a bit of mass at a very high acceleration. All right, now what we'll do is we're gonna try to figure out what these tensions are. And what I'm going to do here is try to make myself a little room. I'm going to take this whole kit and caboodle, shrink it down a little bit, move it up. Okay. All right, now what I'm going to do to get this tension, I need a free body that includes this tension. And there's a couple of choices. Choice number one, I could draw a free body of this. That will include that tension. It'll have a 2,500 Newton force to the left and this unknown tension, 2,500 Newton force to the right and an unknown tension to the left. The other option to get this tension is this part of the system. And I think what I'll do is I'll go ahead and draw a free body of that part of the system, because as far as left and right forces are concerned, that free body will only have one force. Notice that only one thing, this rope, breaks this boundary that's in the left or right direction here. So this free body will only have one force, so one force to the right. So what I'm going to do here is draw a picture of this. Right, so now what I'm doing is a free body again of this part of the system. Now I'm going to go ahead and put in mg, oops, because the system has a weight. And I'll go ahead and put mg here. I'm just going to take note that this mass would be the mass of the system, 150 kilograms. We also have a normal up. Now, these are not the same normals. Again, it's not the same normal as this one. This was the sum of all three. This is the sum of just these two. So this normal represents the normal force on box 1 and box 2. So I think so that notationally this stuff all makes sense. I'm going to go ahead and call this 1, this 2, this 3. This normal in this equation, I'm going to put a 1, 2, 3 there, for it was the normal on all of them put together. This is the normal just up on box 1 combined with box 2. So normal 1, 2. Same thing with this mass. I'll call this mass 1, 2. Mass of the 50 kilogram object with a 100 kilogram object. Right? And again, looking at how we defined our system. This was our system here, and you notice we have a rope coming across that boundary there. So we need to imply or put a force vector in for that rope. Or I should say for the force that rope applies to the system. That is applied right here. This is some unknown tension. And I think I'll call it, because it's the tension between boxes 2 and 3, I guess I'll call it tension 2, 3, for the tension between 2 and 3. It's a pretty simple Newton's second law equation for this. Sum of all forces x direction equals ma. I'm going to go ahead and do right positive. And then we look at our free body. Again, you always look at your free body when you're writing your force equations. That's what the free body's for. So the only force there is tension 2, 3 equals mass of the system, 150 kilograms, times the acceleration of the system. Now, the good news is, as long as this rope doesn't break, all three masses will have the same acceleration, 14.3 meter per second squared. I'm going to go ahead and get a value. I get about 2145 newtons, approximately 2145 newtons. All right, I should point out why there's not a force for this rope. Again, that is an internal force. Go back to the original picture and look how I defined my system. Again, this is my system for that free body, and this rope never crosses this boundary. If I did try to put a force vector in for this rope, this rope is pulling left on this mass, right on this mass, and those two forces would add to 0 anyway. So again, that's an internal force. That's why it doesn't go in the free body. So we've got our tension 3. Right. Next, we want this tension. A couple ways we can get it. There's actually several ways. We could do a free body of this. That will include that tension. We could do this. That also will include that tension. I'm going to go ahead and do this because it's going to be the shortest equation to save me some room. So drawing a free body of only the 50 kilogram mass. And again, I'm going to start by cloning it here. And I'll do this free body. Oh, I can probably get this done right here. This one's going to be short. Okay, that thing's got a gravitational force down. Whoops. Like my force vectors in black. And a normal force up. All right, so we got the gravitational force down, mg. We have a normal up. Now that normal is the normal only on mass 1. Really, this mass here is just mass 1. We have this tension here. That's the tension between 1 and 2, and that tension is acting to the right. And I guess I'll call it tension 1, 2 for the tension between masses 1 and 2. Now we just need to write a short Newton's second law equation. And again, I'm getting this from the free body. Sum of all forces x direction equals ma. Right positive because that's my standard rule of thumb. Identify the acceleration direction, call that positive. So looking at my free body, there's only one force acting to the right. The one called tension 1, 2. And that's going to equal mass, 50 kilograms, times A, which again, mass 1 here also has an acceleration of 14.3 meter per second. And I get for a value here, tension 1, 2 of 715 newtons. Okay, so the purpose of this video is to demonstrate how to cut a system apart and draw different free bodies and apply Newton's second law to the different free bodies. I hope this video demonstrates these concepts reasonably well. Have a great day.